In the previous lesson, I mentioned the Kubernetes control plane, which is the fleet of cooperating processes that make a Kubernetes cluster work. Even though you'll only work directly with a few of these components, it helps to know about them and the role each plays. I'll build up a Kubernetes cluster part by part, explaining each piece as I go. After I'm done, I'll show you how a Kubernetes cluster running in GKE is a lot less work to manage than one you provisioned yourself. Okay, here we go. First and foremost, your cluster needs computers. Nowadays, the computers that compose your clusters are usually virtual machines. They always are in GKE, but they could be physical computers too. One computer is called the master, and the others are called simply nodes. The job of the nodes is to run pods. The job of the master is to coordinate the entire cluster. We will meet its control plane components first. Several critical Kubernetes components run on the master. The single component that you interact with directly is the Kube API server. This component's job is to accept commands that view or change the state of the cluster, including launching pods. In this specialization, you will use the kubectl command frequently. This command's job is to connect to Kube API server and communicate with it using the Kubernetes API. Kube API server also authenticates incoming requests, determines whether they are authorized and valid, and manages admission control. But it's not just kubectl that talks with Kube API server. In fact, any query or change to the cluster's state must be addressed to the Kube API server. etcd is the cluster's database. Its job is to reliably store the state of the cluster. This includes all the cluster configuration data and more dynamic information, such as what nodes are part of the cluster, what pods should be running, and where they should be running. You never interact directly with etcd. Instead, Kube API server interacts with the database on behalf of the rest of the system. Kubescheduler is responsible for scheduling pods onto the nodes. To do that, it evaluates the requirements of each individual pod and selects which node is most suitable. But it doesn't do the work of actually launching pods onto nodes. Instead, whenever it discovers a pod object that doesn't yet have an assignment to a node, it chooses a node and simply writes the name of that node into the pod object. Another component of the system is responsible for then launching the pods, and you will see it very soon. But how does Kubescheduler decide where to run a pod? It knows the state of all the nodes, and it will also obey constraints that you define on where a pod may run, based on hardware, software, and policy. For example, you might specify that a certain pod is only allowed to run on nodes with a certain amount of memory. You can also define affinity specifications, which cause groups of pods to prefer running on the same node, or anti-affinity specifications, which ensure that pods do not run on the same node. You'll learn more about some of these tools in later modules. Kube Controller Manager has a broader job. It continuously monitors the state of a cluster through Kube API server. Whenever the current state of the cluster doesn't match the desired state, Kube Controller Manager will attempt to make changes to achieve the desired state. It's called the Controller Manager because many Kubernetes objects are maintained by loops of code called controllers. These loops of code handle the process of remediation. Controllers will be very useful to you. To be specific, you'll use certain kinds of Kubernetes controllers to manage workloads. For example, remember our problem of keeping 3 Nginx pods always running. We can gather them together into a controller object called a deployment that not only keeps them running, but also lets us scale them and bring them together underneath the front end. We'll meet deployments later in this module. Other kinds of controllers have system-level responsibilities. For example, node controller's job is to monitor and respond when a node is offline. Kube Cloud Manager manages controllers that interact with underlying cloud providers. For example, if you manually launched a Kubernetes cluster on Google Compute Engine, Kube Cloud Manager would be responsible for bringing in GCP features like load balancers and storage volumes when you needed them. Each node runs a small family of control plane components too. For example, each node runs a kubelet. You can think of kubelet as Kubernetes agent on each node. When the Kube API server wants to start a pod on a node, it connects to that node's kubelet. Kubelet uses the container runtime to start the pod and monitors its lifecycle, including readiness and liveness probes, and reports back to Kube API server. Do you remember our use of the term container runtime in the previous module? This is the software that knows how to launch a container from a container image. The world of Kubernetes offers several choices of container runtimes, but the Linux distribution that GKE uses for its nodes launches containers using Containerd, the runtime component of Docker. kubeproxy's job is to maintain network connectivity among the pods in a cluster. In open source Kubernetes, it does so using the firewalling capabilities of iptables, which are built into the Linux kernel. Later in this specialization, we will learn how GKE handles pod networking.